So, welcome to this module on this bone tissue property. In the last module we have discussed about the bone structure, and if you remember that couple of the terms that I have introduced in the last module is that one is that so one of the term that I have introduced is that cortical bone, then cancellous bone. So, cortical bone is that hardest part of the bone, that which is that outside mostly outside part, and cancellous has a more spongy structure. So, this has a very large macroporous structure, whereas cortical bone also has some pores, but it is largely more dense structure. So, it is relatively more dense structure, and because of that typically cortical bone has much better superior mechanical properties than cancellous bone. Other things that if I recall that I have mentioned that there are several canals in this bone structure. So, one is that one is Haversian canal and another one is that Volkmann's canals. So, the function of these different canals in the bones is to transport blood, oxygen, nutrients to bone cells, as well as to take the waste products from internal part of the bone to the outside the bloodstream. Okay, so this is that and these are the things that I have mentioned. Other things that I have mentioned, that typically the structural unit of a bone is more like a known as osteon. So, this is the structural unit of a bone structure, and this osteon that is that hierarchical level of bone structure I have explained at sufficient details. So, this hierarchical level of bone structure, it starts with this how these hydroxyapatite nanoplatelets So, this different level of bone structure or various level of bone structure were discussed in terms of this how these hydroxyapatite nanoplatelets were attached to the collagen fibrils, and these collagen fibrils they make that smaller part of this osteon structure. Then osteon structures are concentric circles. So, these concentric circles are arranged in a very random manner in this entire cortical bone structure. Now, today we will start with this bone composition, followed by different types of natural bone and some aspects of the structure property relationship of natural bone. Remember, the structure property relationship is key to in the material science, because when we consider the different materials, for example, metals, ceramics or polymers. So, their structure property relationship is very important, and therefore, that we need to understand that how the structure property relationship is relevant for this natural bone. So, as far as the gross composition of the natural bone is concerned, so mineral phase is 69% and this majority is hydroxyapatite or some non-stoichiometric hydroxyapatite to be precise. Organic phase, that is collagenous protein phase, this is like 22% out of which collagen is 90 to 96%, And there are several cellular components, 3 particular cellular components, osteoclasts, osteoblasts and osteocytes, which were referred to earlier lecture multiple times. So, osteocytes is the more matured bone cell. And also among this mineral phase, apart from abundance of this, or in addition to abundance of this hydroxyapatite, you have citrate, carbonate, fluorite and hydroxylans, and water is around 9-weight%. So, there are different types of bone depending, and the types of bones essentially essentially reflects on the size or shape of this bone structure itself. For example, long bones, as the name suggests, it is a larger in length. So, it is a tubular in shape, and length of bone certainly greater than the width or breadth of the bone, and consists of a shaft and 2 enlarged curved ends, and this is mostly the cortical bone surrounding medullary cavity. And then examples of this long bone structure is femur, where during this bone implantation mostly people use some cylindrical defects in the femur, and also tibia, humerus, radius ulna. So, these are like other examples of the long bone. So, this is that macro structure of the long bone structure. As you can see, this is a relatively large bone structure, where length of this bone is much greater than the width of the bone. Now, various sections of this long bone structure has been shown. This is the 2D sections. Now, in the 2D sections, you can see that if you take that internal structure, it shows more like a spongy bone structure, and also in the hollow region which goes along the length of this bone structure. So, you have this medullary cavity and you have this compact bone as well. Okay. So, the other examples of the flat bone like calvaria, and then irregular bones, that is facial bone in the skull. So, here you can see that this is a more carved like a bone structure. Now, there is another thing called flat bone structure. So, essentially you have 2 flat plates like structure. So, these 2 flat plates are essentially the cortical bone structure. So, 2 sides is cortical, and intermediate you have a large porous structure, and this is your cancellous bone structure. So, this is a typical morphological features of the flat bone structure like calvaria, scapula and ribs, and it is mostly, although name suggests it is flat, but it is mostly carved rather than being flat. And then unique arrangement of having the cancellous or porous type of structure, cancellous bone structure in between the 2 solid parts cortical structure actually is very helpful, because cortical structure being more dense, it helps in protecting or giving mechanical support to the intermediate cancellous structure. The other bone structures include irregular bone structures, as the name suggests that they essentially does not have any regular geometric shape, and also it consists of a very thin cortical shell surrounding trabecular core, and then examples are facial bone structures. This is the irregular bone structure. Now, this bone, as I started discussing in the last module, so it is the collagen and calcium phosphate based nano biocomposite. Now, the presence of collagen actually provides the bone the required elastic modulus or elastic stiffness, as well as the strength properties. The presence of collagen provide some other set of properties which I will discuss soon. Now, since bone is known as the mineralized hard tissue, mineralized hard tissue means so the presence of calcium phosphate, actually this is considered in the materials nomenclature as the mineral content in the bone. So, in a very normal healthy bone structure in an adult, typically this is like 65 to 69%, and in a older patients normally this mineral content gets lower and lower. So, therefore, since the mineral content goes down, or mineral content is much lesser than healthy adult bone structure, then this the bones in the older patients, they are more prone to fracture or they become more fragile. So, some of the things about the properties of the tissue, that is that properties of the tissues vary between individual and also varies within a same human patient with anatomical location, and this is significantly affected by the degree of mineralization. So, that is something called BMD, bone mineralization density, which depends on the calcium phosphate content or hydroxyapatite or non-circumvented hydroxyapatite content in the bone. And then density of the bone, which largely depends on the calcium phosphate content in the bone, is not an intrinsic property and it changes with time, and that is what I just mentioned, that in the older human patients this density decreases. In other words, this calcium phosphate content in the bone decreases, therefore, they are much more fragile. Now, since bone has a polymer as well as ceramic paste. So, bone also I have mentioned in last module that bone is a unique example of the polymer ceramic based hybrid composite. So, mechanical property wise, bone does show some characteristic features like a viscoelastic behavior of a polymer as well as to some extent brittle behavior of a ceramic material, and that is what is being shown here. So, since it depends on it has a viscoelastic property. So, therefore, this bone should show bone also exhibits the strain rate dependent mechanical property or strain rate dependent mechanical response. What you see here, the lowest curve, it has been obtained the stress strain response when the strain rate is 10 to the power minus 3 per second, 10 to the power minus 3 per second. Now, if you increase the strain rate epsilon dot, if it increases, then what happens in the next case 10 to the power minus 2, the stress strain response goes up. If you go to 1 per second, like 1 per second means 10 to the power 0 per second, then what will happen? It still goes up. That means it still has a unique ability to exhibit constant unique ability to exhibit deformation at a constant stress level for relatively larger or over a larger strain values. But if you go to the very large strain behavior like 10 to the power 2, 3 into 10 to the power 2 per second or 10 to the power 3 per second, as you can see here and here. So, this shift is more towards that up, but also towards the left. So, there are two things that you can see, that with increasing in strain rate, the fracture strain. So, if you consider this is as a sigma f. So, if epsilon dot increases, that strain rate increases, then sigma f fracture strain also increases, but at the expense of the failure strain. So, this is your failure strain. So, epsilon f actually decreases. What is the other thing that increases? That your slope in the linear curve, that becomes that also increases because it becomes much more stiffer and stiffer. So, therefore, elastic modulus also increases. So, higher the strain rate, higher is the strength, fracture strength, higher is the elastic modulus, however, lower is the fracture strain. So, lower is the ability for the bone sample to deform. So, from this stress strain response, it must be clear to you that during high strain impact or during an accident, why a person can undergo bone fracture very easily, because in an accident case, that when the bone experiences very large impact, then it although it shows little bit higher strength, but the fracture strain is fairly low. So, therefore, natural bone is more prone to fracture because of limited plasticity. The other things that you can see here, that typically stress strain response of the bone has two unique components. One is the elastic components and followed by kind of a viscoelastic component. So, this is your viscoelastic component. Viscoelastic means that it behaves like a viscous fluid as well as elastic solid. So, it is a combination of the viscous fluid property plus elastic solid property that makes the bones more like a undergoing constant deformation, undergoing deformation at constant load, and also it shows strain rate dependence. So, normally if a material is purely elastic like a ceramic material, it will not exhibit any strain rate dependence. If a material is polymer, it will show strain rate dependent property. If a material is metal, then it does not show strain rate dependent, because it has a ductile deformation which is essentially attributed to the dislocations in metals. So, because of the difference in the characteristics between metals, ceramics and polymers, polymers is the only material which shows strain rate dependent deformation behavior. In mechanics, in the mechanics literature, it also described as anelasticity behavior. So, it is not like a purely elastic behavior. So, think from this brief discussion, it should be clear to you that bone has a strain rate dependent property, bone has a viscoelastic property, and with increasing strain rate the fracture strength of the bone increases, elastic modulus increases, failure strain decreases, and therefore, bone is more prone to fracture. Now, little bit elements of the fracture mechanics is important, because it will give you some idea that why this bone is prone to sudden fracture. So, this is a rectangular plate. So, rectangular plate has a edge crack, and this crack is shown here like edge crack. So, this edge crack has a length c. Now, you are pulling this rectangular plate with a stress sigma, and so you are applying it by tensile stress sigma. So, what happens everywhere in the plate, like if you take any volume element here, this volume element will experience sigma stress. Okay. Now, if you look at any volume element ahead of the crack tip or adjacent to the crack tip, if you zoom it here, now this particular volume element will experience some stress which is denoted here sigma c. Subscript c essentially denotes at the crack tip. So, that is why it is called sigma c. Now, the sigma c is certainly not equal to sigma. Why it is so? So, although that anywhere else in the rectangular plate this material will experience sigma, but at the crack tip it is not sigma, simply because crack essentially or crack physically is described as the localized region of bond rupture, or in other words, if you have a covalent bond. So, this covalent bond is not directly continuous across the crack. So, it is crack essentially represents some discontinuity. So, it is kind of some structural discontinuity is represented by crack, and because of that this around the crack tip there is something called stress concentration, and the stress concentration has been mathematically expressed here, and what you see here, it is 1 plus 2 into square root c upon rho. So, what is c? C is your crack length. What is rho? Rho is your radius of the crack tip. So, radius of curvature of the crack tip. Now, if a crack is very sharp, then what it means that c is greater than rho, c is much larger than rho, or in other words, if the crack is long or crack is sharp, then that case c, if the c much larger than rho, then c by rho essentially much greater than 1. And if that is the case, sigma c can be approximated as 2 into square root c by rho into sigma. So, what you see now immediately, that stress concentration at the crack tip essentially scales with the square root of the crack size. Okay. So, larger the crack length, more is the stress concentration at the crack tip. And in case of metals, what will happen, that this stress concentration somehow is consumed because of the dislocation plasticity, but in ceramics this dislocation plasticity is not possible. like in case of that hydroxyapatite based materials, and therefore, this crack can go in an uninterrupted manner leading to fracture of these samples into two pieces. So, therefore, it is important for one to understand that the basic concept of stress concentration and how one can determine experimentally is that there are three ways this loading can take place in a cracked body. So, if you remember, this is a rectangular cracked body. Now, this rectangular cracked body, I am showing that what are the three different ways you can load it. One is the mode 1, that is the pure tension. This is the mode 1. Now, mode 2 is the sliding mode, like you are applying shear stress on the cracked surfaces. Mode 3 is also tearing mode, but you are applying the shear stress, but in a direction which is perpendicular to the mode 2 direction. So, out of this, mode 1 is more dangerous. I put a star here. Why I put a star? Because in the mode 1 it is the crack opening mode or tensile surfaces. So, this crack can easily go across the material leading to fracture of the material. So, this mode 1 therefore, it is much more critical, and in case of the mode 2 you see that it is a more sliding mode. So, in case of mode 2 and mode 3 the fracture toughness values are not realistic towards the what fracture toughness one can determine experimentally by mode 1. And this is how this experimentally one can measure. So, what you see here, this is a 3 point loading assembly, this is the 4 point loading assembly. So, if you apply, this is your P by 2, that is the load is distributed at 2 arms. So, this is P by 2 and now what is this resultant force is there is P by 2 and P by 2. So, every action there is an equal and opposite reaction. So, if P by 2 load is there from the top. So, P by 2 load also would be experienced at the two rollers which are kept at the end of the outer span. So, this is if you put a V notch here on the tensile surfaces. So, under this kind of loading configuration any volume element will experience compression at the top surface, and any volume element at the bottom surfaces will experience tension. So, in the tensile surfaces if you now produce this kind of V notch, you see this is the kind of V notch, and this V notch to what depth this V notch will actually extend to into the bulk of the material, that determines what would be the also the fracture toughness of this material. So, idea of introducing the crack on the tensile surfaces is that once it experiences tensile stresses, then from this V notch the cracks will propagate leading to breaking fracture of the fracture leading to the fracture into two pieces. So, and so if you know that what is the load at which this entire sample fractures, if you know what is the total crack length of this V notch, then you can essentially calculate that what is the fracture toughness. So, this fracture toughness essentially means that is the resistance towards the crack propagation. Okay. So, once you this fracture toughness one can write. So, K1C is equal to y sigma square root pi c. So, c is your crack length, sigma is the stress value at which the failure takes place, and k means stress intensity factor, 1 means mode 1, c means critical. So, this is essentially critical stress intensity factor under mode 1 loading. So, often students are confused, they often pronounce this as a KIC. So, KIC is wrong. So, you have to pronounce it as K1C because 1 has a specific meaning, 1 means this is the mode 1 type of loading. Similarly, since you have K1 stress intensity factor under mode 1, one can also designate K2 and one can also designate K3. So, K1, K2, K3 essentially means stress intensity factor under mode 1, under mode 2 loading and under mode 3 loading. So, these are like 3 different kind of loading configuration I have shown in this slide. So, depending on what kind of loading configuration you can define what is the stress intensity factor under 3 different mode of loading. And then criticality condition essentially means that when that external the K1 value is equal or greater than K1C, that means K1C is an intrinsic property of a material, like every material has these fracture toughness values which is independent of the testing conditions. So, that is the critical stress intensity factor. Now, suppose you are applying some sigma value here. Now, compared to sigma values, you have to calculate that what is the applied stress intensity factor, or in other words what is the stress intensity factor due to the application of stress, externally applied stress sigma. Now, once this K1 value is greater than the material's intrinsic property K1C, then the material actually fractures into pieces. So, having said this, I have given some ideas about that what is the what is meant by fracture toughness. I repeat, fracture toughness is essentially resistance to crack growth propagation. So, therefore, you have to first introduce certain cracks in a material and you see that how this crack will now. So, once this you are introducing these cracks. So, then this you have to see that how these cracks propagate along this particular direction, and once the crack propagates through and through into the material is now broken into 2 pieces. And this is what you can do, you can measure experimentally how you can measure the fracture toughness ACVNB. ACVNB stands for single edge V-notch beam. As the name suggests, that means you have to introduce V-notch in one of the edges and that edge is to be placed on the tensile surface. Now, once you produce the V-notch on the tensile surface, then you have to break them in the flexural mode. This is the like a 4-point flexural mode. Instead of this 4-point, you can also keep one single roller here and you can apply the entire load P here. So, this is called 3-point loading. So, you can use either 3-point loading or 4-point loading, but 4-point loading is by far more preferred because here this much region would be under uniform tensile stress. In case of 3-point loading, only a limited region will be under uniform tension. So, therefore, any crack which are present in this uniform stress region, they can simply propagate leading to failure of the entire sample. So, this is how this fracture takes place in case of brittle materials, and that is how experimentally one can measure the fracture toughness of a brittle material like ceramics. So, 3 things that is important for one to remember. One is the stress concentration. So, second one is that K factor, that is the stress intensity factor. Third one is that what is K1C, that is the critical stress intensity factor under mode 1 loading. So, this is more than enough just to understand very preliminary which is required to know about the fracture of the brittle solid like bone, fracture of the brittle solid like ceramic based materials.